lecture 7 of statics. The title of today's lecture is friction and its application. Intuitively you are all aware of friction. This is developed when two bodies are rubbing against each other. For example, our hands, you can experience some heating up of the hands or some impediment to relative motion between the hands. We will define friction as it is a force of distribution. It is a force distribution at the surface of contact between two bodies that prevents possible motion or impedes existing motion between the bodies relative to each other. So, it has two types of effects. First of all, it will try to prevent the relative motion between two bodies, and secondly, if the motion is already existing, that is the bodies are moving past each other with some relative velocity, then the role of friction is to slow down that motion or impede that motion. Let us see how this force and where does it act. For example, I take this case of a box lying on a surface. Here is a box A and it is lying on a plane surface. So, this bottom surface of the box is in contact with this floor, and this is the plane of contact. This dotted pink line shows the plane of contact. Now, if I try to move the box towards right, then the force of friction will be opposing that motion, and this force will be developed which will try to impede that motion, and hence this force will be acting towards left. So, it is a resisting force. On the other hand, if two bodies are curved bodies or at least one of them is curved, then the contact between the two bodies is just a point contact or a line contact. In the previous case, there were infinitely many points of contact. Here there will be much less number of points of contact. Essentially, if it is these are two spheres, there will be only one point of contact. If one is a cylindrical surface, other is a plane surface, then there will be a line of contact. In the example 1, when the surfaces are both plane, then there is a total surface of contact. So, in the second case, we will consider the tangent plane as the contact plane. So, suppose wheel A is moving in a anti-clockwise direction, then the force of friction will be in the clockwise direction. It is always opposed to the direction of the relative motion between the two surfaces. Well, friction is generally undesirable because it causes loss of energy, as you will be learning later on, that when there is a force and the point of application goes through a small displacement, then some work will be done. So, that is the work lost due to friction, but in some cases the force this force of friction is a useful entity, as we will see that it will be very much useful in transmitting power from one point to another point through friction between belt and a pulley, or in clutch thrust bearings, in clutch, in brakes. All these are some of the useful applications of force of friction, but generally it is work lost in the form of heat or sound. It is quite well known experience that when two bodies are rubbing against each other, some screeching sound is produced, as well as if you are rubbing your hands against each other, then hands become warm, sometimes the heat can be very large. There are two types of friction, number one dry or Coulomb friction, and second is fluid friction. In this course we will be in this lecture we will be concentrating on dry friction. Fluid friction is involved in case of lubrication, that is when we try to reduce dry friction by spreading a layer of some fluid or viscous material in the form of oil or a lubricant. So, now let us see what are the salient features of dry friction, how it is produced, what causes this dry friction. Well, the two contacting surfaces, although they may look to be very smooth and plain, actually if you look at those surfaces under proper magnification, large enough magnification, then you will find that there is some undulation or roughness on each of the surfaces. Here I have shown two bodies A and B, and near the contact point we have enlarged the profiles of the surfaces, and let us see, one profile shown green is given over here, and the other profile of the surface is B. Now, due to this roughness there are asperities, the undulations, and these asperities they interlock with each other. Okay. If the surface is absolutely plain, there are no undulations, then there are no asperities, but in general case there will be some asperities, large or small. Now, when we try to move, let us say surface A relative to surface B, these asperities will interlock. They will try to prevent the relative motion unless the force is large enough that the surface A can shear off, cut off those asperities and move forward. Sometimes due to these asperities, the contact stresses can be so large that some heating is produced. Okay. So, there will be local melting at the contact points. So, again when we apply force, at the contact points the material will be removed or sheared off, and that is why when there are two rubbing bodies, rubbing surfaces, some loss of material is always there. This is called wear of the bodies. Okay. So, that is the material, although it may be very small, very less quantity, but some material loss is there called wear and tear. So, now how does this force of friction come into play? First of all, let us say here is a block of weight W which is lying on a level surface, and at that moment we consider the state of equilibrium. There is a downward force W and an upward reaction from this surface onto the block will be force N. W is equal to N. So, and both are in the line of action of W is same as that of N. So, the body is in equilibrium, there is no motion. Now, the same block we try to push with a force P from the left hand. So, it is trying to push the block towards right, and to maintain the body in equilibrium, because the body has not yet started moving, there must be generated an equal and opposite force F, which is at the contact surfaces between the block and the floor. So, this force F is the force of friction. Now, look here, P is equal to F for equilibrium, but the lines of actions of P and F are different. So, they produce a couple. So, this couple will be a clockwise couple. Now, in the vertical direction, W is the weight of the block, it is downward, acting vertically downward. So, there has to be a vertically upward force to maintain the body in equilibrium, sigma F y is equal to 0. So, a normal reaction N exactly equal to W will be produced, but the line of action of this normal reaction N will be such that the distance between the line of action of W and that of N should be such that it exactly balances the couple due to P and F. The couple due to P and F is a clockwise couple. So, the counterbalancing couple between W and N must be anti-clockwise. So, that the normal reaction will lie on to the right of the line of action of W. So, this distance between the two should be such that it exactly balances the previous couple. Okay. So, as we keep on increasing P, the pushing force P which is trying to move the block, the couple is increasing, the value of W and N are same. So, to balance the increased couple, the point of or line of action of N should also keep on moving towards right. So, at any stage the normal reaction will adjust at the distance from W in such a manner that the body is maintained in equilibrium till the critical state will come that N is passing through the edge of the box, because if it goes outside this, then it is no longer acting on the block. So, these are the gradual stages of this simple thought experiment. Now, if we look at the graph between the applied force P and the force of friction developed, so as P is increasing, the force of friction will also be increasing in order to maintain the body in equilibrium. So, the relationship between P and F will be a straight line as shown over here, till a point is reached that the force of friction cannot exceed that state. So, that is the state number 1. This is the just below it, the body is about to move, about to have a relative motion with respect to the floor on which it is sitting. So, starting from 0 friction, the friction force is gradually increasing to the maximum. This state labeled as state 1 is the state of impending motion. If you increase the force P just beyond this state, the body will start to move towards right in this experiment. As soon as the motion is started, then the force of friction will immediately go through a decrease, that is, there will be a jump discontinuity. So, earlier the force of friction was Fs, that is static friction, that is the state of impending motion, and once the motion has commenced, the force of friction will be the dynamic friction, Fd. And always remember that this dynamic friction is less than static friction, and this state will be called the state of slip. So, remember, state of impending motion, state of slip. Now, within the context of Coulomb friction, let us examine what are various laws governing this friction. First of all, the total force of friction that can be developed is independent of the magnitude of contact area. You remember in earlier diagram I gave you 2 examples. In one case there was a finite area of contact, between two plane surfaces A and B. In this case, the area of contact is very small, or theoretically it is 0 area of contact, even if it may be a line contact, but the area involved. But the force of friction is, it does not mean that the force of friction here will be 0. So, it is independent of the contact area, it depends on so many other factors. Number 2, the frictional force is practically independent of the velocity, or if the relative velocity between the sliding bodies is not very high. Unless it is very high, then there is some dependence on the magnitude of the velocity. For moderate velocities, it is independent of force of friction is independent of the magnitude. Also, the sliding friction force is less than the impending slip condition force, as we have already seen, because Fs is less than Fd. And thirdly, the total frictional force that can be developed is proportional to the normal force transmitted across the surface of contact, that is the normal reaction. So, the force of friction is proportional to the normal reaction. As we have seen in the previous discussion, this is proportional to, so this is a straight line relationship. Well, the third law is put in a mathematical form. F is proportional to n, n is the normal reaction. So, we can write it F is equal to mu s times n, where mu s is the constant of proportionality and called coefficient of static friction. F is the maximum force of friction, as we have seen, that is the force at the impending slip condition, and n is the normal reaction across the contact plane. When sliding is already taking place, that is the slip condition is achieved, then same law is still applicable, but the constant of proportionality is now different. Now, Fd, this is F static, Fs, and this is Fd, the dynamic friction is equal to a new constant mu d, which is the coefficient of dynamic friction into n. Okay. And since impending slip force of friction at the state of impending motion is greater, so the coefficient mu s is greater than the coefficient mu d. Now, how to visualize this coefficient of static friction or the state of impending slip? A very simple experiment is helpful in understanding this. Suppose you have a plane, a level surface which can be made more and more inclined, that is, you start from the horizontal, as we have here a horizontal surface, and you imagine there is a smooth plyboard plank and there is a hinge. So, when the plank is gradually lifted, the angle of inclination of this plank becomes more and more. So, this is the phi is the angle of inclination to the horizontal. On this plane board, you have a given box whose or given surface whose coefficient of friction is to be measured. Always remember, the coefficient of friction is a characteristics of two contacting surfaces. It is not a property of one surface, but it is a property of two contacting surfaces. Let us say one surface is wood, the other is steel, or rubber and steel, or wood and aluminum, etc., etc. So, here is a block of weight W, and it is lying on an inclined plane whose inclination is gradually increased, and a stage will come when the block will start sliding down. onto the surface. Okay. So, at that stage, when it is just about to slip down or slide down, the angle of inclination is phi s. Okay. Let us examine, you can say just before that state is reached, the state of equilibrium of the box, that is the block has or block or box has not yet started to slide down, but it is about to, that is the state of impending slip. So, at that stage, let us see the triangle law of forces for equilibrium. There is a downward force of W, there is a force N normal reaction which is normal to the surface over here, okay. And then there is a force of friction F which is along the plane of contact. So, drawing the vertical W normal to the surface and along the surface, we can complete the triangle, and then the inclination between W and N is the angle of friction or static friction, and it is designated as phi s. Well, we can see from the triangle law of forces, F divided by N is equal to tangent phi s. You can easily verify it because F and N are mutually perpendicular. So, this is 90 degrees. So, you can easily see that F divided by N is the tangent of the angle phi s, or phi s is tan inverse of F divided by N, and by third law of Coulomb friction, F divided by N is the coefficient of friction mu s. So, the phi s, which is called the angle of static friction, is nothing but tan inverse of the coefficient of static friction. And similarly, we can examine when the body or block is sliding down the inclined plane. Same problem, but now you can say that this block is going down this inclined plane at a uniform velocity, then the angle here will be, which will be able to maintain a uniform velocity, will be slightly less than phi s, it will be angle phi d. And same equations of equilibrium and the triangle of forces will give us the result that F divided by N is equal to tangent of phi d, that is the angle of dynamic friction. So, phi d is equal to tan inverse of mu d, and obviously the angle phi d is less than phi s because mu d is less than mu s. Let us fix our ideas more firmly by looking at few of examples. The first example I am considering is a block of mass 27 kilograms is to be pulled up an inclined plane as shown in this figure. Here is a inclined plane, this is the horizontal plane. Okay. The angle between the two planes or the inclination is 30 degrees. This block is to be pulled up the incline through a lever shown here with the force P, and the inclination of the lever is angle beta to the direction of the movement. Find and taking the coefficient of static friction between the block and the incline as 0.25, find the smallest value of P for which the motion of the block is impending, that is the block will just start to move up. And secondly, what is the angle required, that is angle beta, which will pull the block up the incline. First of all, let us see the coefficient of friction mu phi s is given, and this is equal to coefficient of friction mu s is given, and mu s you know is tangent of the angle of static friction, that is phi s, or in other words phi s is tan inverse mu s. So, this angle will be 14.4 degrees. Now, as we have done in the previous analysis, again we have a block, a rectangular block shown here. The weight of this block is mass times acceleration due to gravity. So, 27 g is the vertically downward force due to weight, and then there is a normal reaction and the force of friction. Okay. So, since the block is to move up, the direction of impending slip is upward. So, the force of friction is downward. So, the normal reaction and force of friction being two vector forces, here is normal reaction, here is force of friction. So, the resultant of these two forces will be resultant R. So, this resultant R is shown, and the angle between the two, as we can see from the triangle law, is the angle phi s, and the force P which is trying to pull the block up is shown here, which is inclined at an angle beta to the direction of motion as shown here, and this direction of motion is at 30 degrees to the horizontal. So, completing the triangle law, we will have the vertical force W and the normal reaction R, and since the problem says what is the smallest value of P which will cause the impending motion. So, from this point what will be the shortest distance? Thinking geometrically, there are two vectors W and R, and from this point what will be the shortest distance, so that this corresponds to the minimum force. That will be the along the normal direction, that is a line which is at 90 degrees to the resultant reaction R, resultant of force of friction and normal reaction. So, this from this point we will draw a normal to the direction of R, and that will complete the triangle of forces, and this will give us the minimum force which will be capable of pulling the block up. This is the geometrical solution. You can do it analytically also by assuming an angle alpha and then minimizing it, minimizing the force. So, for P to be minimum, P is perpendicular to the resultant R, and when will it be perpendicular? When beta is equal to phi s, because remember that the angle between two lines is equal to angle between their normals. This 27 g force is normal to this, and this is normal to P. So, whatever the angle here, same is the angle over here. Okay. And at that stage you can calculate what is the force P by sine law of triangles, that is, this is the sine law, we have to find out P. So, P over this angle of 44.04 degrees is equal to W over sine of 90 degrees, right. So, you will have P is equal to 1877. So, when the lever in the pulling lever here is inclined at the same angle as the angle of static friction, that is 14.4 degrees. At that stage, the force, pulling force which will be required to move the block will be minimized, and its value has also been obtained as 1877 newtons. Now, let us have a look at another problem in which you have more than one contacting surfaces. For example, here is a incline and there are two blocks A and B. Okay. They are both lying on this inclined surface and also they are in contact with each other. So, two boxes A and B weighing 500 newtons and 300 newtons respectively are placed on a plane whose inclination is gradually increased, just like our mental experiment, from horizontal to angle theta. This is the angle theta. Find the maximum theta so that boxes just slip down the plane. Take the coefficient of static friction between box B and the plane as 0.2 and that for box A and the inclined plane as 0.3. So, different coefficient of frictions are applicable. Let us see, we want both the boxes to slip down. Okay. It cannot be that only one box. Suppose we imagine that box A slips down, but the box B does not slip down. As soon as the box A slips down, B will also slip down, because now this force, the contact force between A and B is removed when they are no longer in contact with each other. So, there will be a force when they are in contact, there is a contact force up the plane. As box A moves, that force is no longer there. So, box B will be slipping down automatically. Similarly, when box B cannot slip down unless block A or box A also slips down. So, both these boxes will slip down simultaneously. So, consider the free body diagram of the upper box, that is box B. Now, what are the forces acting on this? There is a gravity force of, that is the weight of the box, 300 newtons, okay. And then there is a reaction R from box A on the left of it. So, a normal reaction between A and B is R. So, which is trying to push the box B up the incline. Now, at the time of impending slip, because the slip is about to take place down the slope, so the force of friction will be opposing it, that is up the slope, and this is the normal reaction. So, these are the 1, 2, 3 forces and 4 forces acting on the box, and if you consider the equilibrium of this box B, sigma of all the x is parallel to the incline and y is perpendicular. So, sigma f x is equal to 0. So, r plus f is equal to the component of this force of 300 newtons in the x direction, which is 300 sin theta down. So, and similarly sigma f y is equal to 0. So, this n is equal to 300 cosine theta. So, these two equations to solve for two unknowns, and then free body diagram of the box A. Then again by Newton's third law, there is equal and opposite reaction coming from the box B onto A. The reaction is R. Again force of friction between the two surfaces, that is surface of the box A and the incline is F dash. The weight of the box is 500 newtons, again sigma f x is equal to 0, sigma f y is equal to 0. So, you write down similar equations. So, you have these two equations from the previous, and also at the state of impending slip, when the motion is about to start, by Coulomb's third law, F is equal to the static coefficient of friction 0.2 times the normal reaction, this is for box B, and F dash for, that is force of friction acting on the box A, is equal to the coefficient of friction, which is 0.3 times the normal reaction N dash. So, total we have 6 equations to solve for 6 unknowns. What are the unknowns? 2 forces of frictions, 2 normal reactions, the normal reaction between A and B on the height surfaces, and angle theta. Okay. Well, you can easily do it, that is from here and from these two equations you can substitute for f dash, and in the previous two equations you can substitute for f. So, then you can eliminate n dash etc. and n, and ultimately it is very simple analysis to come to the final equation, in that is after eliminating r also you will have the single equation 800 times tan theta, tangent of angle theta, is equal to 210, or theta is equal to tan inverse of 21 by 80, that is theta is 14.71 degree. So, you see that by repeated use of Coulomb's friction law, we can solve for the angle required, which will be just sufficient to cause the slip. Okay. If we increase the angle slightly, the two boxes will start slipping down this plane. Well, now you might have observed one thing. In the problems which you have taken up, only 2 equations of equilibrium were used, that is sigma f x is equal to 0, sigma f y equal to 0. Whereas, we have learnt when we were discussing the conditions for equilibrium, that if the forces are plane forces, then 3 equations of equilibrium are to be satisfied. Sigma f x is equal to 0, sigma f y is equal to 0, and the moment of the forces lying in that plane about any point, that is sigma m z about point O, any arbitrary point O is equal to 0. So, why only 2 were involved? Why not the third equation? Because in all these problems we did not know or need to know the exact line of action of the normal reaction N. It was not of our interest or concern to find out where the normal reaction was going through. It was going through between the two surfaces. Okay. Normal reaction is always in the contact area, it cannot go out of the contact area, that much is sure, but otherwise whether it is at the center or towards the right of the center or left of center, we did not need to find out. Now, there are certain problems, very interesting problems, in which we need to know or we have to guess the line of action of the normal reaction. Okay. So, I will take up analysis of one such problem where the normal reaction, a critical state of normal reaction will be required, beyond which the body can topple over. and this is illustrated with a simple example like this. A heavy crate weighing 1 kilonewton is to be pushed on a floor with force P. So, this is a box or a crate lying on a surface. The base of this box is 0.5 meters. A force P is to be applied in such a way that it does not topple the box. You might have experienced when you try to push a heavy table, if you push it too high, then the table or the chair tries to topple over. So, similarly, if I push it at a sufficiently high point, then the box may topple over around this corner. Okay. So, what is the highest position h at which P needs to be applied for moving the crate without tipping it or toppling it? So, that if I apply the force P slightly higher than that position, it will rotate around a corner. The coefficient of static friction between the crate and the floor is 0.25. Okay. So, let us look at this problem. Now, as I mentioned earlier, the crate will not topple or tip as long as the line of action of the normal reaction N lies within the base of the crate. So, as long as it is, because you can see here is force P and the opposing force of friction will be towards right. So, they are creating a anticlockwise movement. Now, the weight downward is passing through the center of gravity of, let us say, through this point, and as the normal reaction is acting here, here or here, there will be a clockwise moment. So, to balance this anticlockwise moment should be exactly equal to the clockwise moment, and as the point P is higher and higher, more moment is created. It means the point of line of action of N will move more and more to the left, till a stage reaches when N is exactly passing through this tip, through this corner. Because if I increase force even slightly more, N will go outside the base of the crate. So, this is the critical state. So, let us examine the state of equilibrium at this point, that is a normal reaction at passing through the corner, force of friction, a gravity, a force downward, and the pushing force P. Again, this state of equilibrium, what are the conditions for equilibrium? Sigma Fy is equal to 0, that is the normal reaction N minus downward load of 1000 newtons. So, it gives us N is equal to 1000 newtons. Sigma Fx is equal to 0, that is P is equal to F, that is obvious, and then the moment about this corner point, where we could have taken moment about any point, but this corner point is most convenient, because two forces are already passing through this point and their moment about this point will be 0. So, I need to take up moment of P and moment of 1000 newtons only. So, when you do so, F into H, that is moment this is force P. So, I think I yeah. This will be P into H, that is the pushing force into H is equal to the moment due to the gravity force 1000 into 0.25, 250, and also the force of friction is equal to mu times static coefficient of friction times the normal reaction. So, this pushing force is 250 of course. So, both P and F, they are 250 newtons at the impending slip, and what is the highest point at this stage? 250 by 250 is equal to 1 meters. Okay. A third example where we have to imagine in what direction the relative motion is going to take place. From the looking at the geometry of the problem, we have to examine what is the stage, how the motion of various surfaces is going to take place. So, here is a system of two blocks, block A and block B. There is a inclined wedge like surface. So, at an angle 20 degrees to the horizontal. So, block B is resting on block A on this inclined surface, and also block B is resting against a stopper on this surface. Okay. So, there are three surfaces involved: the surface between block A and the floor, the surface between A and B, the surface between B and, you can say, this rod C. Okay. So, the coefficient of friction between all contact surfaces is given as 0.2 static friction, and determine the force P needed to pull the block A towards right. So, I want to pull it underneath this block B, and you can easily imagine that if this block A is moved towards right, this block B will be lifted up, because the contact point is moving like this. So, it will be more and more height will be produced. Okay. So, as the block B moves up, so there will be a relative motion between B and C. So, there are three relative motions involved. So, at the impending slip, as we have said, of block A to the right, block B will tend to move upwards, and accordingly direction of friction or friction forces are chosen like this. So, between block A and B, since the block B is going to move up, and it means that a point on this will be moving in this direction. So, the force of friction will be along downward and to the right, and there will be equal and opposite force on the block A. So, you can imagine that if the normal reaction between the block A and block B is N2, again both are equal and opposite, the forces of friction will be mu N2 and mu N2 over here. Of course, the weights of the blocks 1000 Newton and 2000 Newton are given, and then I will look at the situation at the bottom surface of block A, because this block is moving towards right, the force of friction will be towards left. N3 is the reaction from the floor to the block. So, this at the impending slip, the force of friction will be mu times N3, and finally, on this surface against the rod C, since the block B is moving up, the force of friction will be downward, and let us say the normal reaction is N1. Okay. So, it means on both these blocks the forces are now completely known. This is the free body diagram of block B, this is the free body diagram of block A, and let us apply the conditions of equilibrium. First on block B, sigma Fy is equal to 0. Well, most of you have enough practice with this. Let us see what are the vertical forces and what are the horizontal forces. Sigma on block B, vertical forces, a downward force of 1000, downward force of mu 1, which is again because all the coefficients of static friction are equal to 0.3 or 0.2, yeah 0.2. So, you have 0.2 times n1, that is downward, this is downward, and then n2 will have a vertically upward component, that is n2 times cosine of 20 degrees, and similarly this will also have a vertical component, this inclined force, that is mu times n2 times sine of 20 degrees. Okay, this will be downward. So, if you look here, you will have minus 1000, this is 1000 newtons, not n, sorry, 0.2 times n1, n2 cosine 20 degrees minus n2 sine 20 degrees is equal to 0, and this is sigma fx. Then they consider the horizontal components. There is n1 here, a mu n2 times cosine 20 is the horizontal component, again n2 times sine 20 degrees will give me a horizontal component. So, that is the equation number 2. Similarly, you consider the equilibrium of block A. So, again vertical upward force, a downward force n2 times cosine 20 degrees. Similarly, mu times n2 times sine 20 degrees will be giving me vertically upward component, and similarly you can consider the horizontal forces. So, by considering various vector components, you come to these 4 equations. Okay. Now, there are 4 unknowns, and you can solve for these 4 unknowns. From 1 and 2 you can solve for n2, and then the force required to move the block A towards right comes out to be 1318. The normal reaction N3 from the floor is also obtained, that is 3137 newtons. Okay, and N2 is, this is no longer required. Now, there are certain class of problems in which you have to make a logical decision about whether the force of friction will be downward or upward, or how the bodies are going to be moving with respect to each other. So, various cases have to be examined one by one and then decided. So, some alternative solutions have to be examined, and some of the solutions will be feasible, some will not be feasible. So, what we mean to say is you have to come to some logical choice. So, such problems are very often encountered, and in our next lecture I will be taking up one such problem in which the direction of force is not known beforehand, a priori means beforehand, and then based upon equations of equilibrium we will see that what is the appropriate direction of motion, and under that condition what are appropriate forces. So, that we will take up next time. Thank you very much for your attention in this lecture.